All right, let's get right into it. Today, we're going to talk about the surprising link between a classic card game and, believe it or not, the single biggest hurdle facing the future of artificial intelligence. And it all starts with a game that's known for being just ridiculously complex. And no, that is not an exaggeration. We're talking about the trading card game Magic: The Gathering. Researchers have actually proven that inside the normal rules of a tournament legal game, you can build a theoretical working computer. It's insane. And if we can wrap our heads around how that's even possible, we can start to see one of AI's deepest, most fundamental weaknesses.
So, how in the world does a deck of cards become a computer? Well, the answer goes way back to the very birth of computer science itself.
It all comes down to this idea called Turing complete. It's named after the absolute legend, Alan Turing, who came up with this idea of an abstract machine that could solve any algorithm you could possibly throw it at. If you can build one of these so-called Turing machines inside of a system, doesn't matter if it's a programming language, a video game, or even a card game, then that system is considered Turing complete. It can basically compute anything. So how'd they do it in Magic? Get this. Researchers Alex Churchill and his team used a line of creature tokens on the battlefield as the computer's memory, its tape. One single creature acts as the head, which reads and writes the data on the other tokens. And the program? It's this mind-bending Rube Goldberg machine of card triggers that all go off automatically, step by step. It's wild. It means a game of Magic can be, mathematically, as complex as any system can possibly get. But as complicated as all that logic is, there's a totally different kind of reasoning that trips up even our smartest AIs. It's something we humans do without even thinking, and it all boils down to one simple phrase you've probably heard a million times. Correlation isn't causation. Okay, check this classic example. On the left, we've got a correlation. The data is clear. People who carry lighters are way more likely to get lung cancer. A simple pattern matching machine would just stop right there. But on the right, we have the real cause. We all know the lighter isn't giving people cancer. It's just hanging around with the real culprit, smoking. Humans get that difference in a heartbeat. And that right there, that simple leap from just seeing a pattern to actually understanding why the pattern exists, that is the massive brick wall that today's AI keeps slamming into. So if looking at a bunch of data can be so misleading, how do scientists ever prove that one thing actually causes another? They can't just trust the correlations. They have to get their hands dirty and run an experiment. The gold standard here is called a randomized control test, or an RCT. It's actually pretty simple. You take a big group of people, you randomly split them in two, and then you apply some kind of change, the treatment, to only one of those groups. By randomizing everything, you control for all the other variables. So any difference you see in the end, you can be pretty darn sure it was caused by that one thing you changed. You found the cause. Now that's awesome for testing a new drug or a new website design, but what about the really big questions? You can't just A/B test the global economy. You can't rewind history and see what would have happened if you did something different. You're just stuck with the messy, real-world data you've got. And that data is just filled with hidden traps. The biggest trap of all is something called a confounder. You can think of it like a hidden puppet master, secretly pulling the strings on both the thing you think is the cause and the final effect. It makes it look like they're connected when they're really not. Here's a super simple example. Let's say we look at some old data and notice people who took this special elixir recovered from the flu faster. Wow, a correlation. But hold on, what if younger people were just more likely to try the elixir, and younger people also just get over the flu faster anyway? In that case, age is the confounder. It's the real reason for the recovery, and it's creating a totally fake link between the elixir and getting better. So, to get around these confounders, scientists have to think in counterfactuals. It's a fancy word, but it just means what-if thinking. For every single person who took that elixir, they have to try and guess what would have happened if they hadn't taken it. And for everyone who didn't, they have to imagine what would have happened if they had. This kind of what-if reasoning is the absolute core of finding a true cause. Okay, let's bring this all back to AI. Why is this specific kind of thinking, this what-if stuff, such a gigantic problem for models that have been trained on basically the entire internet? Well, it's because large language models are, at their core, just enormous correlation engines. They are absolute masters of recognizing patterns. They're trained to predict the next word in a sentence, which is all about finding associations, not understanding causes. They can tell you that people who carry lighters get cancer, but they don't truly get why. And this limitation becomes a huge, huge roadblock when we try to build what everyone's really after, true AI agents. Systems that can actually act on their own in the world. For an AI to be genuinely useful, it can't just follow a script. It needs autonomy, it needs to be proactive and set its own goals. And to do any of that, it has to understand how its actions will cause things to happen. And hey, don't just take my word for it. The researchers over at DeepMind said it perfectly. They proved mathematically that for an AI agent to adapt to new situations it has never seen before, it must have a causal model of the world. Understanding cause and effect isn't just a cool feature, it is a fundamental requirement. And this really gets to the core difference between us and them. Humans, we're theory-driven. We build little mental models of how the world works to predict what's going to happen next, even in situations we've never been in before. Current AI, it's the total opposite. It's data-driven and backward-looking. It's stuck just finding patterns in stuff it's already seen. So what's the big deal? What does solving this causality problem actually unlock for humanity? Well, the answer is pretty much everything. I mean, think about it. Building AI that can reason about causes would completely change science, letting us find the real triggers for diseases. It would transform economics and medicine, helping us figure out which policies and drugs will actually work. And it would finally give us robust, reliable AI that we can actually trust to make important decisions. This is the next great frontier in technology. But here's the reality check. We are not there yet, not even close. This research from Apple is super interesting. It shows that even these newer, more advanced reasoning models, which are designed to kind of think before they answer, they eventually hit a complexity wall. They do great on medium-hard problems, but when things get really, really complex, they have a total collapse. They just break down, same as the standard models. Which brings us right back to where we started. The insane complexity of a game like Magic isn't just about memorizing all 20,000 plus cards. A great player builds a theory of the game in their head. They anticipate what their opponent might do, they adapt their strategy on the fly. All of that is causal reasoning. So the ultimate question for AI isn't just about feeding it more data. It's whether we can ever teach it to truly understand the rules of the game.